Welcome back. For 2.1, our objective is to find the derivative of a function using the limit definition of derivative. In this first part, you're not going to find this in the handout, so just sit back and relax and take in the fact that what derivative means is the slope of the tangent line. And that's what derivative means, the slope of the tangent line. So here you see a function. This is our parabola. We'll call this parabola f of x. And the red line is a tangent line. It is tangent, let's say, at the point x sub 1. And I need to find the slope of that line. Well, how do we find the slope of a line? That's right, we need 2 points. So for the slope of that line, we need 2 points. And if we have 2 points, then we can say, sure, I know how to find the slope. Slope is y2 minus y1, or change in y, over x2 minus x1, or change in x. But I don't have 2 points here. So what can we do to make it have 2 points? Well, sure, pick another point on it, but I don't know where that random point is in space. But if I know the function, I can say, well, let's pick a point on the function and connect to that first point. And then if I draw that line, I can find the slope of that line. It's not the tangent line, but I can find the slope of it because here I have one x coordinate and here I have another x coordinate. Therefore, I know the function value that goes with it, which is our y value, and the function value that goes with it, which is our second y value. And I can write this as f of x sub 2 minus f of x sub 1 over x sub 2 minus x sub 1. And I can say there's the slope. It's almost the slope of the tangent line because those lines have a very close slope, but it's not. That line that's connecting 2 points, that's a secant line. So we just found the slope of a secant line. I want you to visualize it another way. Let's say between x sub 1 and x sub 2, there's a change in x, or we can write it as delta x. So another way to visualize the bottom is to say, the denominator is to say delta x. Now, if we're going to call this delta x, another way to describe these x coordinates right here, instead of x sub 1 and x sub 2, is to say x sub 1, or x, and its neighbor, so this guy we're going to call just x, and x sub 2 we're going to call x with delta x added onto it. Similarly, we can then rewrite these y coordinates to f of x and f of x plus delta x added onto it, f of x plus delta x. Well, how does it change what our difference quotient looks like? Instead of x sub 2, it will say f of x plus delta x, and instead of x sub 1, it'll say f of x. So here's another way to see the slope formula, f of x plus delta x minus f of x over delta x. You need to know how to see it both ways. Again, though, this is just the slope of the secant line. So how do we get the slope of the tangent line? Well, if instead of having picked a point way away from the first x like this, we pick it a little bit closer, like this. Now if I connect those 2 points, what do you notice? That's right. The slope of the green secant line looks now a little bit more like the slope of the red tangent line. And if we visualize now where x and the second x value is, or x plus delta x, they're a little bit closer together than they were at first. But it's still not the exact same slope. So what can we do? That's right, pick a point a little bit closer to that first point. So you've got your first x coordinate and your second x coordinate even closer together, or shrink delta x a little bit more. But that's not even good enough. So pick a point that's a little bit closer and a little bit closer, and to the point where it looks like they're right on each other. What are we doing? Well, here's the 2x coordinates. We shrunk delta x even more. Now here are the 2x coordinates. We shrunk delta x even more. Now we've shrunk delta x so much that it looks like delta x is nothing, or rather, delta x has approached 0. So how do we change from the slope of the secant line to the slope of the tangent line? That's right, use limits. The slope of the tangent line is this difference quotient or this difference quotient, but using limits. Either we can say, if we use this difference quotient, the limit as the second x coordinate approaches the first x coordinate of f of x sub 2 minus f of x sub 1 over x sub 2 minus x sub 1. Or we can say, using this difference quotient, the limit as delta x gets so small it looks like it's approaching 0 of f of x plus delta x minus f of x over delta x. And this right here is called the derivative. So it's very important to remember graphically, derivative means slope of the tangent line. Analytically, this is the limit definition of the derivative. F prime of x means the derivative. Notice our difference quotient and the limit as delta x goes to 0. This part right here, this limit definition, is the slope of the function, f of x in this case, at all x values. The slope everywhere in the function's domain. This particular one, notice that we're plugging in an x value c. This particular one, which comes in two forms, is the slope of f of x at one x value. In this particular case, that x value is c, how I wrote it here. This with f prime of c, notice it's a little bit of a different form. This one is what I will be referring to as the alternate form of the limit definition of the derivative. Now it's important that we make a note that this alternate form can only be used when you know the point. It's not for the derivative at any x value or at all x values. It's for the derivative at just one x value, only used when we know a point. Directions say use the limit definition of the derivative, and I have to specify because soon we're going to find other ways to find the derivative. Use the limit definition of the derivative to find the following for each function, then describe what you're finding using words. Check part B by using the alternate form of the limit definition. So first I want you to think of what is f prime of x. It is the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. This is a must know. You must know this. Memorize, memorize, memorize. Well, if we want to know f of x plus delta x, let's use f of x and find that first. F of x plus delta x, use a different color for that. This part right here, f of x plus delta x, I'm going to do in green. F of x plus delta x means take out wherever x is, and in its place, put x plus delta x. So 6 times x plus delta x squared minus 7 becomes, well, let's leave it like that. We can simplify it in that limit definition of the derivative. So now I'm going to go back to this limit definition, and I'm going to write limit as delta x approaches 0 of the green part that I did above, 6 times x plus delta x squared minus 7. Then the rest of it minus, now f of x is 6x squared minus 7, all of that. Notice how I'm using parentheses, all divided by delta x. Now we need to do some foiling, some expanding, and some distributing. And when we do that, we get the limit as delta x approaches 0 of 6x squared plus, we get 2x delta x's, so multiplying by 6 gives us 12x delta x's. Delta x squared times 6 is delta x 6 delta x squared minus 7, so that was all the part That was in green. Then I'm going to distribute the negative here. So negative 6x squared plus 7. Now remember the trick we talked about when you do these difference quotients? Anything that doesn't have a delta x will subtract out. 6x squared minus 6x squared, negative 7 plus 7. Notice that what's left only has delta x's, which means now we can do some factoring. Take out the delta x. We have 12x plus 6 delta x left over. That delta x we took out can factor out of the top and the bottom, and we can now do direct substitution, replace 0 for delta x, so 12x plus 6 times 0 becomes 12x. That is the derivative. This is the derivative, or if we are going to describe what we're finding using words, this answer right here of 12x, 12x is the slope of f of x at all x values, because we can plug anything we want in there for x. Now let's take it to part B and plug in the 3. So 12x is f prime of x, so 12 times 3 is 36. So the way we answer what that means is 36 is the slope of f of x, but only at x equals 3. The slope of f of x at x equals 3 is 36. Alternately, let's check using the alternate form, which is the limit as x approaches c of f of x minus f of c over x minus c. This is at a specific point. Remember the derivative at c. So ours is the derivative at 3. Remember up here, we're checking using the alternate form. So the derivative at 3 is the limit as x approaches 3. F of x is 6x squared minus 7. F of c is 3 squared minus 7 all over x minus 3. If we simplify the top, we get limit as x approaches 3 of 6x squared minus 54 over x minus 3. The top can then factor, where if we take out the 6, we're left with x squared minus 9, which factors into x minus 3x plus 3. Notice we can factor that out, and now we can plug in the 3 into here, and we end up with 6 times 3 plus 3, or 6 times 6, or 36. Same thing that we got doing it the other way.